Thank you so much for tuning in. This is my talk about my AMSI.fail project. We're going to start off by, I'm going to introduce myself first. I'm going to talk a bit about AMSI. I'm going to talk about the project, how you can use it, how you can integrate it with your operations, and why I think it's a profitable project for the community for a whole. Yeah. So let me just start off by introducing myself. So my name is Melvin. I go by the alias Langvik online. I used to be a C# developer, worked a lot with the Azure Cloud architecture, a lot with the especially Azure Functions, storage account, custom database, stuff like that. I did a lot of integrations for customers in Norway. And then I wanted to move over to the offensive security side. So I started as a penetration tester for BDO cybersecurity in Norway. And I work there now. I will be working there out of the year. And then next year I will be moving over to TrustedSec, which is super exciting. So I'm super hyped for that. Some of my previous projects, which you may or may not have heard of, Sharp Collection, Sharp App Locker, Sharp DLL Proxy, and Better Safety Cats. So that's just short about me. So that's, I mean, AMSI has been talked about so many times before, so this is probably going to be something you've heard before from other talks, but I just have to go through it just so everybody can tag along. So let's start off by talking about AMSI. So AMSI is short for Anti-Malware Scan Interface, and it allows applications and services to scan script-based content for possible malicious events. It's released and maintained by Microsoft, and it's completely open for anybody to use. So any application can call it, any service or application can register as what's called an anti-malware engine for AMSI. And this may sound different from what you've heard before, but in a typical context, an anti-malware engine is typically Windows Defender, and an application submitting data for AMSI to scan is something like PowerShell or with as of late C# as well as VBScript. And I think F-Secure really sums it up in a later blog post they created. So I'm going to go through that part of them. Took a lot from them in this talk. So when PowerShell creates a process for PowerShell specifically, when PowerShell creates a process, AMSI DLL is loaded from disk, and functions in AMSI DLL is exposed via system management automation. So the C# library, system management automation, is basically every core functionality in PowerShell itself. And within that library, there's a class called AMSI utils. That's where it goes from C#, which is the management automation DLL, to native, which is the AMSI DLL. That's where AMSI DLL has the functions exposed into the C# class. And within AMSI.dll, there's a function known as AMSI scan buffer. It's essentially the function that is used to scan the script's content for potential malicious content. So every command that you run in PowerShell will be supplied to that function, and the content will be scanned, and if it's deemed malicious, it will be blocked. So it's pretty much that simple, right? This may explain it a bit better. So on the top, we can see PowerShell, VBScript, potential or application. They all have some sort of integration with AMSI.dll, right? So they can use many functions, but two of the core ones are AMSI scan buffer and AMSI scan string. So PowerShell will talk with AMSI DLL through system management automation, and VBScript and other applications can talk to AMSI DLL directly, natively, or also use some sort of integration DLL between to go from, say, C# to native. So information is provided to AMSI, and then on the other side, on the right side, you can see that some sort of service has to be registered to take a look at that information and deem it malicious or not. So in like the classical example, in the vanilla cases, that is Windows Defender. So Windows Defender is registered as the anti-malware engine. It takes a look at the data that AMSI provided, and it tells AMSI this is bad, this is not bad, and then the execution flow continues or stops. This is what it looks like. So on the top, you can see that I try to, well, I don't really try to run the command, but I try to type something in. I know that that string I typed in has signatures in AMSI or in Defender. So the data is submitted to AMSI. Defender takes a look at it, says nope, and then that message is returned. This script contains malicious content and has been blocked by antivirus software. So that's how an AMSI block would look like in PowerShell. On the right side, that's how an AMSI block should look like in some Office applications. That message may vary some, but looks something like that. And on the left side, you can see Windows Defender, the logs that it gives when it detects, well, in this case, it was an AMSI tamper script, and script that tries to get around AMSI, but it also basically takes the information that is provided by AMSI and logs it and blocks it. So it shows up there as well, not only in the PowerShell view. So when it comes to breaking AMSI, this is nothing new. This has been known for quite a while, and it's at this point it's publicly used and known every day, I would assume, right, by actors. So the techniques to break or disable AMSI, as I said, has been discovered. They typically involve patching specific functions or variables within the loaded libraries that utilizes amc.dll or amc.dll itself. So in the case of PowerShell, the bypass we're going to look at later breaks a functionality in the system management automation library, but some of the C# bypasses break functionality in the actual native amc.dll library. And the main reason we are able to break or look at AMSI at all is that it lives on the same level as the threat, right? So when amc.dll and system management automation operates in PowerShell.exe and we execute code in PowerShell.exe, we technically have unconstrained and unrestricted access to its own memory space, which means that we can mess with every library loaded in that process, right? We can control it. And that's, at least from the integration to amc.dll, that's one of the main issues. It's on the same level. We can reach it from an attacker perspective, unlike EDR solutions and CM solutions, right? They operate on kernel level. Many of the methods can be translated across PowerShell and VBScript and C#. That is true for some, but not for all. And some of the contributors include, Adam, XPN, Manifestation, Rastamouse, and amsec. So I think Rastamouse and XPN both sort of had the C# patch going, where they would locate a specific function in amc.dll and patch the return code, the opcode. I know amsec translated a lot of that over to PowerShell, and Manifestation is basically the bringer of amazing PowerShell snippets that does that also breaks AMSI, but in a slightly different way. So that's sort of what we're going to take a look at now. So in May 2016, Matt posted a tiny PowerShell snippets that basically breaks AMSI for the entire PowerShell process that you run it in. So anything after that command won't be detected as malicious, even if it is. It gives you free reign. And what this PowerShell snippet really does is that it takes a variable or property called amc.fail in system management automation, inside a class inside system management automation called amc.utils, and it sets that property to true. And within its own logic, that will cause we can take a look at it on the next page, but that will cause a specific function to return result not detected for anything that you put into it. Which effectively blinds PowerShell's integration with AMSI, as I said, after you're under command forever. So this is pretty good gold. Let's take a look at how it looks in terms of code. So in the system management automation AMSI.utils class, there's a function called scan content. This is the function that PowerShell calls every time it wants to look for malicious content. Every time we run the command in PowerShell, it's piped through this function, and AMSI will determine if it's malware or not, whatever we are trying to run, right? So you see, you have the input, the string content input, and then you have a if section here that says if the AMSI init fail variable is true, it will return result not detected. And this is what we mess with. So this is logic that already exists, but the variable that it refers to is always set to false. But so Matt uses reflection to set this variable to true, and therefore AMSI will always return result not detected. And this is key, right? So if we take this bypass, if I just copy paste this bypass from Twitter, and I paste it into a PowerShell window and try to run it, it won't work. Right, so this is from 2016. The functionality works, but it's detected as as malicious, obviously, right? So specifically, this AMSI utils part has a signature detection. And even if we attempt some basic invoke obfuscation commands, it will still be detected. Now, of course, if you combine enough functionality in invoke obfuscation, you will get around this, but it will completely break size limits. It will make the clean one-line AMSI bypass into a huge script, which it may in some cases not be really good. So let's take a look at the amc.fail project that I sort of created to solve this and sort of mainstream and finalize the way we use AMSI bypasses. So the amc.fail project is a free online service that produces small PowerShell snippets that break or disable AMSI. Each snippet is randomly, well, when you generate snippets, they are picked from a very small pool of variations, and then they are applied a custom or a very specific set of obfuscation, a tailored obfuscation, as I say, before it's given to you. And this way, you won't find any signature detections for these as of now, and it will just simply work, right? So it's an Azure function as of now. It's C#. It's an HTTP trigger that's in the cloud and that you can use. So it's online at amc.fail, and the source code is also on GitHub. Yeah, it looks like this. So you can go to amc.fail, and then you can click generate, and you will be given some different snippets of code that they should never be the same. The signatures shouldn't collide. Of course, at some point they will collide, but they shouldn't. And they will get past current signature detections and patch AMSI for you for the current process. And let's talk about how does this work. It isn't really advanced at all. I like to keep it KISS, keep it simple, stupid. I mean, there's no reason to make this more complicated than it is. So there's sort of two key elements. Each snippet or each variation of AMSI bypass that it uses, I've picked out keywords that I know are signature detected. So one of those snippets could be AMSI init failed, which I know a defender hates. That's like a really hardly signatured snippet. And then I take out those keywords and I obfuscate them or encode them in some way. And I also do that to some random keywords in the same technique, sort of to create variation. And I try to also pick out the keywords that I know are specific for the technique, because there's really no need to pick out keywords that are super generic. Like Defender can't create signature detections for something that is used in a non-malicious way. That would be way too aggressive, and it would break a lot of existing legitimate applications. So they have to be very careful when they pick up signatures. That's why I also only take a look at the keywords I know are specific for the AMSI bypasses. Sounds simple, it is simple. So these are the three main encoding methods that I sort of use within each other and combined. So you have HTML encoding, you have a combination of char and byte encoding, and then you have diacritics, if I can say that right. So for HTML encoding, it's pretty straightforward. It takes pretty straightforward there. For the char and byte encoding, it gets a bit more interesting. So the char sort of array that we get that out of takes an input as an int value that is the ASCII value that we're looking to get. So a capital A, the ASCII value for a capital A is 122 minus 57. Can't do that in my head right now, no way. But that's the ASCII value for a capital A, and the ASCII value for a lowercase m is 184 minus 75, and the list goes on, right? So it sort of randomizes the ASCII value that the char represents with both minus, plus, division, and multiplication. And in that way, we're able to sort of encode, I guess, the AMSI keyword and not having to write it plainly, and AMSI is fine with that. For diacritics, it's almost the same. So basically what we're doing is that we're normalizing, I'm not so sure about the naming for it, but basically the weird capital or lowercase a's and o's that we find are one of many, but when normalized, they go back to a single O, right? So So when I do the obfuscation for this, if you take a look at the source code, I have a capital A. Let's find and pick out some random other foreign language capital A's. For example, you have the one with the 2 dots. That's one variation. And you have one with a single slash on top. That's one variation. And both of these, when normalized with PowerShell, goes back to a capital A. And sort of you randomize that string. And when normalized again, it goes back to the clean version. If you take a look at the source code that's posted on GitHub, it uses these within each other. So it's not always just like a single char encoding or only byte encoding. As you can see here, we have a byte encoding within a char encoding to sort of mix it up a bit. And this is profitable in terms of getting around signature detection and getting AMSI patched. And as I said earlier, when AMSI is patched, you can do whatever you want, to a certain degree at least. So on the top picture here, you can see that I tried to write out in PowerShell, defender hates AMSI init failed. AMSI picks this up, gets it in, and the defender says nope. And then we get back, the script contains some malicious content, blah, blah, blah. And then you run the AMSI bypass. That goes fine. You don't get an error when you run that, and then you try to run the same command that you couldn't run earlier, and it works. You can run it. So AMSI has successfully been patched. And these are one of many use cases that I can think of in terms of both on engagements, on CTFs, on labs, as well as from an operational perspective. So the easiest way would be just to copy and paste it from the website, statically copy it into whatever payload you're trying to deploy, and you're fine, right? I guess if you want to mass generate payloads, you can also use the API directly. Or if you're in a CTF or lab scenario, when you're on the target machine, you can just call the API directly. Now, of course, you shouldn't do this on engagements. This is not great. I mean, in terms of OPSEC considerations, you have no idea what sort of code you're actually running on the target machine here, because you're calling my API, and you're receiving an AMSI bypass that you are invoking, but you can't see it and you can't confirm what you're getting. So this is a huge fail in terms of OPSEC, and you should never do this on the target machine, on the real engagement. But in terms of CTFs and labs, it's an easy way to get around AMSI, right? So after that is ran, you can also type the same command and it won't be blocked. And there are some other couple of interesting integrations that you could do. So the code is C#, so you can easily take this out and add it or modify it, make it better, and add it to C2 frameworks like Covenant or Rasta Mouse Upcoming. Is it Sharp C2, for example, to get a AMSI bypass going for PowerShell if you have a PowerShell stager. You can also use it. You can spin up the API yourself and talk to it directly privately. You can translate the code to Python or JavaScript. The best would be to have this as JavaScript on the client side, so nobody can sort of wonder what's actually running in the backend. But when I created this, it was C#, since I'm the most familiar with that. And you can integrate it all forms of ways with C2 frameworks or with other specific solutions that you might want to use it for. So yeah, go check it out on GitHub. And that's basically it. Thank you so much for your time. Questions, all up, hit me.